Good. So today we will talk about convolutional neural networks. We will cover most of the common architectures, and we'll what the trends in the convolutional networks for classifications, how they work, and what actually we will also overview the papers that are explain the trying to interpret to understand why convolutional networks work so good. But before then, I actually want to some of you asked me to revisit about the course, and actually to do some to summarize and overview about what we learned until now and what we will learn in the rest of the course, of course. So we started from introduction to deep learning, talked about linear models, multi-perceptron, some non-linearity, and why it's important. Today we'll talk about convolutional neural networks, then we'll talk about how to train neural networks, optimization techniques, neural networks convergence, and etc. After then, we'll talk about sequence models, how to work with text, and what the trend there, including state-of-the-art methods for text classification, text understanding. Then we will start talking about unsupervised models. That in the first, until then, we will talk about supervised models, models that we have labels. We will talk what we are about models, what we are about the problems that we have no enough label data sets, and how to do it unsupervised way, maybe self-supervised way, and semi-supervised other methods. And then we'll talk about actually image synthesis. So how we can synthesize the images by ourselves. Then we talk about deep reinforcement learning. Actually, we have only one lecture about it. We will talk about the common trends there and how we use deep networks for reinforcement learning scenario. Then we will talk about graph neural networks. So it's how to learn not on images or non-Euclidean spaces. And I will show you that it's a very important task, and a lot of domains could be benefit by doing that, by using convolutional neural networks with this extension. And then we will talk about actually the hardware part, and we will start it from deep neural network compression techniques, algorithms how to make your networks more thinner and more efficient on hardware. And then we'll talk about a little bit about hardware for neural networks. Then it's all our course, so we have a lot of topics there. Any questions about the course schedule outline?
Will we learn about variational autoencoders?
Yes. We will. Variational autoencoders we will learn when we will learn about image synthesis.
Okay. Thank you.
Great. So convolutional neural networks. So what we want to do? So we have a image, and we want to classify them. Yeah. So the classification of the image is actually, we first take our image, and then we applying some neural network layers, and then we want to see to which class it relates. Yeah, and of course we want to predict the right class. Yeah. So we will learn actually this mechanism, yeah. So all this mechanism from image until prediction. It's we have various neural networks architectures that or convolutional neural network architecture. We will talk about convolutional neural networks today. How did they do it? So outline of today's lecture. So we will start from building blocks, some motivation and history, why it started, and why we have hype over convolutional neural networks. And we will talk about the generation of convolutional architectures, starting from AlexNet, starting of the hype, and ending by MobileNet's family. Okay, so neural network for images. We have input. So as we know before, by multi-perceptron architecture, we have input layers, features. Then we have some hidden layers, and then we calculate the output layer by the number of output tensors is the number of the classes that we want to predict. So we have our image, we have fully connected, and we have image, and actually this is the calculation of the input on the right weight will give us the next tensor. So neural networks for images, we have image, and we have filtrate, we have another image, and we have here weights. Yeah, this is weights. We actually learn we make some filtration on the image, and then we have the output. This tensor is the output of the multiplication of our weights on our input image. So this is the name of this layer. It's feature map. Okay. And I will show you later about which information each of the feature maps in the deepest, when we're talking of deep neural networks, is cover. Okay, so what the information each of the feature maps are handled. Yeah, so we actually taking each new feature map in the same layer. It's taking various of weights, sets, and making filtration on the image, okay? So the new set of learning weights give us new feature map. So the number of the feature maps of the specific given layer is the number of the various weights parameters that multiplied on our input data. Okay, great. So actually, you know, about convolution, when we are talking about convolution itself, it's like, you know, like making filtration on the signal. So in deep neural networks, convolution we define it like feature extractor. Okay, so we have image, and the information regards this image we can extract using convolutions. So this is actually taking one filtration of this image will give us some. This is some output, okay? And then we are taking this weights and filtering the given image will give us feature map. So this is the output of our feature map. Okay. So taking another image again, we'll take another feature map, and etc. etc. Actually, here this is actually the K feature maps of applying bank of K various filters. Okay. Question regards it?
Is it a fixed bank of filters?
Oh, this is a good question. Of course, these filters are learned. This is the parameters that the neural network will learn. And the question that you may ask, how I initialize these parameters. So what's the start? Yeah. So we have a few options to initialize it, and there are a lot of proposed algorithms how to efficiently make this initialization. Okay. Most of the cases and some the simple way is to taking some to do it randomly from taking from some Gaussian distribution, and then we can sample weights. Okay, but we have some more efficient way to do it, and there are a lot of papers that propose more and more efficient initialization of weights for image classification tasks. Good. Okay. So, okay. So the convolution layer. What is convolution layer? Convolution layer. We have our convolution layer. It's making filtration. Yeah, and then applying non-activation. Okay, so first we make filtration by multiplication, and then we applying non-linear activation. In most cases, in convolutional networks, we use ReLU. I defined what is ReLU. ReLU is actually the simple activation that for all the values are cut in 0. And if you below 0, it's cut. If you above 0, it's the real number, the real value. Okay, so filter f by k filters, we make from them our next feature. Okay, so we have L features maps in the next layer. Okay, why we have L feature maps in the next layer? Because what the answer, guys?
Because we have L filters.
Okay, I will repeat the question. The question: if we have k feature maps in the existing layer, and we applying L filters to this feature map, how many feature maps we will have in the next layer?
L
feature maps, because the number of the feature maps depends on the number of the various filters that we apply in the previous layer. Yeah? Good. Okay. So this is how it, okay, very good. So this is how it works. We have our values, and then we make infiltration. So this will be the first filter, and then it will be the second filter, and etc. etc. We each time after we calculate, we actually making the calculation, and then we calculate the output feature maps, and the number, and the of course the feature map size depends on how we do our convolution. So if we want to preserve the size, we will do convolution by padding the contours. If we want to reduce the size, we use strides. Strides is actually our step size, yes? Good. Questions about this? Good. Okay, so efficient implementation of convolutions is actually how to do it, how to effectively do it on your hardware. So actually what we are doing, we reshaping all the images in our neighborhood in columns. Okay, so we have image to column comparison. So, and then we do matrix vector multiplication. Okay, so if we take our D by K by this is our filter by C matrix, then we actually apply each of us on the feature maps, and we make the matrix multiplication between our filters and our images. Okay, of course, then after we have our convolutional neural networks, we do backpropagation. So our backpropagation is actually, we have, yeah, so we first calculate our function, our nonlinear function of x, and depends on our input and the weight, our parameters. And then we will derivative it respect to weight and respect to our input. Yeah. So of course, we have here a channel. We talked about it last lecture. So we have two derivations respect to W parameters and respect to X input. Okay, so yeah, so first we calculate the derivation respect to weights. When z is, we assume that our filter is indexes go from -f to f, yeah, and then we actually can calculate this way, yeah, and we can find all our derivations for all weights. Yeah, very good. Again, it's mathematician that we talked about it last lecture with regards to MLP. The same one works on for convolutional neural net, for the convolutional layers. Good. So, and then we have our arrow depends on parameters. It's actually arrow depends on z and multiply by the input x. Yeah, very good. Okay, so I will skip it. Okay, good. So which layers we have in convolutional neural network? So once we did our, we start from doing filtration on images, then applying ReLU. Yeah, but what we want to do when we want to change our dimensionality of our the size of our images and the numbers of our feature maps. So what we are doing, we're using max pooling layer, okay, or pooling layer. It's called also average pooling layer. So how pooling layer works? We have k feature maps, and then we are taking some slice of them. See here, like f by f pooling filters and stride s, and then we taking the maximum values of each this stride, yeah, and this will actually be the number of the k feature maps that we have on the updates is actually the resolution of one divide on the stride that we define is actually what will be the output features, size. So first we want to define what will be the output, and then we define what will be our size of max pooling layer. Okay, so we will actually what we will going to do in practical, we will take matrices, and we will take the maximum values of the activation there, and we'll pass it to output. Otherwise, it will be removed. Okay. Questions about pooling? So usually, common practice. What I mean, usually, our f is 2 or 3, and our stride is 2. Okay. So again, and when we do our backfill pass, our gradient from the next layer is actually passed back only to the unit with our max value. Yeah. Why we don't want to pass it to other values? What do you think? It's open question, guys.
Because they didn't affect the forward passing?
Yes, because they didn't affect, because these values will be removed from in the forward pass. So why you should you will not give. It's actually useless because you will not see they are not participate in our final prediction. So the gradients, our loss, it's not dependent on them. It's like parameters that are not depends on our function. Our function it's not variables of our function. Understand?
Can I ask a question?
Sure, yeah.
You said in the beginning of this slide that the reason we use pooling to begin with is because we want to reduce dimensionality. Why do we want to reduce dimensionality in the first place?
Oh, you ask great questions. Great question. Look, when you're doing, okay, so in this lecture, we're talking about convolutional neural networks for a classification, yeah? So you are starting from image. Your image has some dimensionality, of course. It's it could be, let's assume some, I don't know, resolution by 500 by 500, yeah? What you want to do is to eventually classify this image, okay? So the reason why you're reducing your dimensionality, because you want to get some information, some only efficient information about your image for classifying this image for specific class, okay?
Okay.
Again, in few slides, we will talk about the full architectures, and then I will explain again this issue. Okay.
Okay.
Good. Okay. Right now, I'm only talking about building blocks, and then we will talk about all the architecture together. Okay. So let's take about the summary. We have input images, convolutions. This is our alert parameters, nonlinearity, and special pooling, or special pooling is actually called for reducing the dimensionality. And eventually we got our feature maps. So that feature maps, it's the outputs of our hidden layers. So the all images, or we call it feature maps because images, when we're talking about image, we are talking about only the input to the neural networks. But all the hidden inputs of the next layers are feature maps. Okay? Good. So if this is the input, and this is what we got after applying first layer, so this will be the input to the second layer, etc. Good. Please don't hesitate to ask questions. Okay, so again, this is the nonlinearities function. We have ReLU, and we have a LeLU. In convolutional neural networks for classification, the common practice says using ReLU, because LeLU, the difference between ReLU and LeLU, that in the LeLU we have also some representation for negative values, yeah. But for LeLU only, why to use LeLU? It helps for image synthesis. Okay, so only when we will talk about the image synthesis, generative neural networks, then we will talk. Then we will explain that in these cases, LeLU give better performance rather than ReLU. But in the convolutional neural networks, common practice says that ReLU is most efficient, and between trade-off of computational complexity to the result activation. Questions? And we have also ELU. Again, it's it's a more exotic extension of ReLU. People usually do not use it for convolutional neural network classification tasks. Okay, so this is actually our special pooling, and we're taking our filtration this way, of course, and after we got the result, we're applying nonlinearity, and then we doing max or average pooling for reducing our size of feature map. Great, so summary, what we've seen. We have image, applying convolutions, pooling, and then we have convolution pooling, real pooling, convolution, real pooling, until we done to do our feature extraction using convolutional neural networks, and then we use fully connected in the fully connected only in the stage when we want to do classification, only for prediction, okay? And of course, here we have prediction. So the prediction, so this we have here 4 classes. So this value is the softmax result. So it's actually from it's percentage. Actually, it's probability to which class this image is fit. So if you can see, this algorithm works good because he thinks he predicts in most of the cases 94% that it is bot, and it is really bot. Okay. So this is the prototype of convolutional neural networks. Most of them look like this, with some special editions that we will talk about today. Good. So yeah, that's softmax we already talked before. So the softmax converting from nominal values that we have in all our networks to some distribution, yeah, some probability. Good. So now we will talk about the different neural networks and from 2012 until today. So the history started from Jan LeCun. Jan LeCun, he is godfather of the neural networks. So in 1998, he proposed to classify MNIST. MNIST, it's digits written datasets using convolutional neural networks. Before then, people do it in using some traditional machine learning algorithms like perceptrons. Okay. So so he proposed to do. So this is actually the architecture that he proposed, and this name is LeNet. Okay, why LeNet? Because the author was Jan LeCun. So LE, this is from his name. Okay, and network. Why it's 5? Also, people ask. I think that it's not because he didn't propose the versions from 1 to 4. So this was the his first version. This is actually the first convolutional neural network for classification that anyone proposed. So he used average pooling, and here he used sigmoid or tangents nonlinearity. Actually, people now do not use it, and in today's neural networks. So and then he had 5 or 4 convolutional layers and 2 or 3 fully connected layers. Okay, and he classified digits. Yeah. And of course, he got the results was he classified in 95%. His prediction, his accuracy was 95%. Believe before it, the numbers was I know maximum 16%. So it was huge gap. Huge. He actually beat the standard way, the previous methods by far. Okay. Okay, so then people start to build synthetic data sets for image classification, yeah, And the data set that we will talk about, that most of all of the networks that you will see their settings, their topology is fitting for this data set. This is most important data set for image classification that we have from 2012 until now. Okay, and people wants to classify it as good as to build networks to achieve better accuracy on this dataset. So this is ImageNet. So it contains about 1 million training images, and it have 100 classes. It's actually he was labeled by Amazon Turk and by people. A lot of people used. A lot of people labeled these datasets for getting really good labels and not noisy labels. Then Kaggle make competition that people actually build neural networks for achieving better results on this classification. So we have actually 2 metrics for measure the accuracy of image classification on ImageNet. One is top 1, so it's actually to classify, making one classification. And the second one is top 5. So top 5 is actually we are taking 5 images and accuracy on 5, averaging on 5 image classification. Okay, so AlexNet, it's the first feasible solution for classification of ImageNet. So who is Alex? Yes, so Alex Krzyzewski was Jeffrey Hinton student. It actually was his master work. So he built neural networks that can fit. Actually, he can fit GPU. These days, he had GPUs with 4 or 2 gigabytes memory. So he fitted his network for the specific GPU. Okay. So what he done? He split the network. So this is his architecture. So we have 7 hidden layers. We have here 60 million parameters. And he proposed also GPU implementation with speed up 15 times more over rather than using CPU. Okay, and as I said before, he trained on 2 GPUs and it took a week. So 1 week he trained. This network is training for getting the results. Okay, the original results was I think that top 1 accuracy was about 57%. Okay, please keep this number in your head. Okay, so 57%. It was it's AlexNet achieving this accuracy on classification on ImageNet classification. Okay, he also proposed dropout regularization. What do you mean by dropout regularization? So dropout is during training, we drop in some probability, some of tensors, some of feature maps for getting better regularization. Guys, questions until here? I want any feedback. Does it clear? Have any questions regarding it?
Yes, all clear. Thanks.
You're welcome. Okay, so then, yeah, so we talked about, so then every year Kaggle had competition for betting better and better for building neural networks, for beating the previous year results. Okay, so now I will show you. Now we will talk a little bit about what the intuition and or actually the visualization of what happens in the feature maps levels okay? From this, what happens when we're going deeper, yeah? So paper that his name is Visualization and Understanding Convolutional Neural Networks, won best paper award in top-notch conference ECCV. They actually tried to visualize what happened in the neural networks in different layers. So actually, if you are looking on the what you can see in the after first layer, after you're applying filtration of the first layer on your images, you got some. This is actually what you got. So actually, the first layer can distinguish between very high-level features. Okay, so it can distinguish between I don't know, Earth and sea, and you know, dark and sunrise. So it's not really the first layer not really see more details of the images, only very high level details. Okay. Okay. So here, actually, what this paper has done. So they took this first layer, feature maps. They choose the biggest, 8 feature maps with biggest value. And then they did the convolution of these layers. What is the convolution? The convolution, it's like a convolution that you're making filtration. The convolution is regeneration. So we want to recreate the images, the original images, for getting results. And as you can see here, it's exactly what we done. What the convolutions of first feature on first layer does, it's detect some very high information about the images. You can see here, I don't know, sky and sea and other very high level abstraction features. Okay. Then when you're going deeper, the second layer. Yeah, sorry. So the deconvolution of the second layer actually give you more information. As you can see here, we have some more information about the image. We can see here, I don't know, trees and birds, more information. So when we do the convolution from the more deeper stage of neural networks, we see that actually this in this stage we detect more and more low-level information about our image. Okay, so this is actually our feature maps of the second layer, yeah, and this is the extraction of the convolution. And the third layer, you can see better resolution. Here you can see also birds and some food. Actually, more and more layers in deeper and deeper stage detect more low-level information regards your original image. Okay, and for layer number 4, it's even more better. And of course, if we go deeper, we will see more and more information. 5 layer, more information. Eyes, we can see eyes and contours and the faces and more and more. Okay, so actually, once you observe this, you observe this paper, we can realize that convolutional neural networks working in the following way. The first layers are detecting high-level resolution features, and the deeper layers detect more low-level resolutions. And finally, we actually in the final layer before the classification, we actually can, by reconstruction, reconstruct the original image. Okay? It means that we learned all information with regards to our image for making the right solution and for predicting the right the information that we want to predict from the given image. Okay? Questions about neural network visualization? So after the AlexNet hype and actually the neural networks that give some best results on this way and also achieve some best results in 2012, and they also proposed how to make the acceleration using GPU, came VGGNet. VGGNet, they proposed more deeper neural networks rather than AlexNet. Yeah, so we have two options for VGG. VGG 16, it means that we have 16 neural layers, and VGG 18, that we have 18 layers. So this is actually the gap between the AlexNet and VGG is very huge. If AlexNet, I think that, see it, the results we can see here. No, okay. So if the AlexNet achieved 56% accuracy, VGG achieved about 16.8 until 17% accuracy on top one of ImageNet. So of course, so the VGGNet they won Kaggle second place and Kaggle competition. So and their topologies, we now will talk about their topology. So we have first we have our input, then we have max pooling, convolutions from 64. This is the number of feature maps. All the convolutions are filters 3 by 3, and then we start from 64 feature maps until 5012 feature maps, and then we're doing our max pooling before fully connected, and this is fully connected layers that are converting from our tensors to classifications, predictions of softmax. So our sequence of deeper neural networks work good. More layers give us better accuracy. That means that the previous assumption of the deeper layers give us better information regarding the more accurate information or feature about our images are right. Okay, so also they propose to reduce the 7 by 7 convolutional neural networks that was in AlexNet to 3 by 3 convolution, and of course it's give a huge speed up and reduce the number of the weights. But this is very huge. The VGGNet have a huge number of parameters. So the smaller version have 16 millions, and the deeper version have I think about 100 millions of parameters. Okay. So also they was the first that experimented with one-by-one convolutions. Yeah, they use it only for a few. They use it only for a few layers, but they started to use one-by-one convolutions, and you will see that the trend with one-by-one convolutions will be higher and higher these days. They actually started to experiment what will happen when we use the small kernels. Okay. Okay, good. Now we'll talk a little bit about convolutions. So one by one convolutions, actually, we have convolution layer. So we have our feature maps, and then we applying one by one is actually one filter. So we are taking filtration by actually summing one. Yeah. So it's not actually averaging. We have one for one output. We have F by F computations. Okay, good. So, yeah, very good. So, what actually the difference? So, linear convolutional layer is actually with it's when we are talking about taking all the input to all the output for feature map, for calculating one output. Yeah, but we also can use MLP convolutional neural networks. So we between the one layer and the other layer, we can use some MLP, some fully connected calculations for getting the output results. Yeah. And we also can experimentize with some hybrid layers. So what done in network work that they saw that using some hybrid net topologies can achieve better results and capturing more information. Okay. So in 2014, GoogLeNet, that he won the Kaggle competition, realized or give one perspective that we need to go deeper. It means we should do more and more deeper neural networks for achieving better results. So they proposed. So the architecture is actually work in the head two major aspects. The first is the inception models, and the second that we actually have parallel passes from the previous pass to the next layer, and these parallel passes actually we are playing with different receptive field size of our our image, yeah, and it means that we can capture more and more interesting and sparse pattern correlations that we can within our feature maps. Okay, so we have parallel paths of convolutions that we are taking one by one convolution, 3 by 3, 5 by 5, and then we concatenated their knowledge, and this way we are increase the receptive field of the convolutions and finding more interesting feature maps. Is it clear, guys?
I have a question.
Of course.
In the tutorial, you showed us that you need to have a bypass from a layer to the next layer because of vanishing gradients.
Yes. We are not yet there. This will be our next architecture. It's ResNet.
Okay.
Sure.
I have a question.
Yeah.
In the case presented here, we have different kernel sizes for the convolution.
Mm-hmm.
Do they also give us different layer size or picture size?
No. Again, as we can understand that convolutional kernel size, it's not reflect on the feature map size. Yes. So it's not defined. Convolutional size not define the feature map size.
Is it because we use zero padding or something like that?
No, it's not. it's not, no, zero padding is for preserving the contour, yes, but it's not really, all matter is the stride, yes. So if you use convolution, if you take assumption that we use padding, yes, and it depends, of course, the size of padding of if this is 1 by 1, 3 by 3, or 5 by 5, yeah. So for 3 by 3, you will need one pixel padding over the contour, yeah, and 5 by 5 it's 2, yeah, and,
okay,
etc. But all the internal pixels, it doesn't matter if it was what the kernel size, yeah. It's only the output feature map. It depends on the stride of your convolution, yeah.
Okay, if we use a stride length that is more than 1, so the 1 by 1 convolution also misses some of the pixels to begin with?
If you, I don't really, can you repeat, please?
If we were to use a stride length that is more than 1, we have one of the examples here is using a 1 by 1 convolution.
Yeah.
I assume that means a 1 by 1 kernel size. So that means we're gonna just skip a part of the previous layer. Is that correct?
No, it's skip layers, not you skip pixels.
Pixels,
Yeah, you not really you don't really skip layers. You skip filters. You skip pixels or feature maps indexes. Yeah, if we can talk about it in the internal layers. Yeah, of course. But you don't using striding. Using strides in convolutions, it's very common way. In convolution in the layers, it's very common to do it because this way is better way to making a dimensional reduction rather than using pooling layers. Yeah, some of the information it's not really important. Yeah, so if you do it in stochastic way, so you're actually covering all the pixels. Yeah, so it's okay. So you will detect all the information that you need. Okay.
Okay. Good. Thanks.
So no, you're welcome. So again, so we have so this is our GoogleNet topology. Concatenation and of using various filters in the same layer. Okay, and here you can see actually this is the old topology from the input to output. This is huge number of layers. We have a few different topologies of GoogleNet, but it's more than 20 or 40. You have 20, 40, 50 layers. But 50 layers deep of our convolution. Yeah, but as you have one of you mentioned before, yeah. So this is and this architecture is named by inception models. So all our networks is actually by building one inception model, and then we can replicate this inception model for building more and more layers, deeper networks. So, yeah, and yeah, that's important. So, yeah, I think that I will give now some intuition. So, but again, they add more and more layers. Yeah, they add a lot of number of layers. But one of the problems in using in adding vanilla convolutional layers, so like adding more and more layers, is that we have a problem with gradient vanishing. So it means that if you the gradients with respect to when you calculate your gradients, the numbers when you're going deeper are smaller and smaller. So it means that it's very hard to find the correlation, to find how specific layer is reflected to the output, to the loss. Yeah. So it means that you add more computational, but adding more layers, but you don't really, in most of the cases, you don't really get better results, because if your gradient's very small, it means that the impact of this learning is quite small. Yeah. So it means that if we want to really build very deep networks, we need to solve this problem. Okay, and in a few minutes I will show you the first solution of this problem. Okay, so there was an Inception v2 and Inception v3. So the difference between them that they use Bayesian normalization. About Bayesian normalization explicitly I will talk in the next lecture, but Bayesian normalization, it's one of the common way to fight against overfitting, or getting actually it's a layer that help to converge of neural networks. Okay, so actually it's reducing importance of auxiliary classifiers. Okay, so more variants of perceptions models with more aggressive factorization of filters we have. So it's actually, you know, you can this way define a lot of different topologies. Okay, so this was actually the ImageNet challenge. So we got these are actually results on different tasks of the Kaggle these days. Okay, so in 2015, it was actually really breakthrough. People understood that after GoogLeNet, and people understood that you cannot really add infinite number of layers. Or you cannot add, or adding 14 layers, it's not really much better than 20 layers, because the gap between the computational gap and the accuracy improvement was very small. So one of the way to overcome it's to use new architecture. And actually, yeah, we started the first AlexNet. It was with 8 layers, VGG with 18, and this paper proposed 152 layers in one of the configuration, of course. So this is really deep. How can we going so deep? And the answer, yeah. So the girls cry because she saw that someone can build this one. Yeah. Okay. So the basic block that give us the opportunity to make deep neural networks, deep neural networks, is residual block. It's basic block and how it builds. We have our input X, we have filter, we have ReLU, and what we do here is we're taking our fx and we concatenate the values of the previous layer. This way, we actually introduce some dependencies, but it's not special dependencies that convolution can find. It's hierarchical dependencies, yes, because we add knowledge from one layer to another layer, and this bypass, it's crucial for and help to build very deep neural networks. It means that in these networks, the gradients are in the deep layers are efficient, so they help to make better performance. Yeah. So this basic block is actually basic. It's a residual block. Yeah, and deep residual model or it's actually the bottleneck. Bottleneck is one block of like Inception in GoogLeNet. It's one block, so we have convolutional layers with the same feature maps, and then you make a skip. Okay, and this way we can build a lot of layers. So let's see of the common of the all ResNet topologies. So it's from ResNet 18 to ResNet 152. Again, most of the difference between them is the number of how many replications you do of the your residual networks of the residual blocks. So here, the difference between here and here, it's actually by factor of the numbers of the residual blocks. These residual blocks is appeared. Okay, and yeah, so it was a breakthrough. It's CVPR best paper from 2016. Questions about ResNet, guys? Okay, so if I will talk about a few training tricks. So what we didn't mention, yeah. So we mentioned way to do deeper networks, but a few tricks that actually we should be aware about them for converge our model. It's how to do initialization. What is regularization or normalization of our data that will help us to the model to converge. Some training data augmentations. Ensemble of networks, averaging the classifiers over the multiple crops flips. This is, this is the small details, but they very efficient when we are talking about how to make the network to converge. So from 2015. Image classification is not part of the IELTS VRC challenge. But people, of course, continue to do it, their benchmark on the data by themselves, by presenting their papers, sending their papers to conferences. Okay, so let's take a look on this plot. So here it's actually number of operation or our complexity. Computational complexity of networks, and here is our result. So as you can see, AlexNet, as you can see, VGG have a huge number of computational complexity because it's, and the more newest architecture actually like ResNet and here we achieve better results by less computational complexity because we use more efficient kernels, smaller kernels, and we do not use a huge number of fully connected layers. So all ResNets are used only one fully connected layer, and VGG networks, so you have few fully connected layers. These layers have a lot of parameters. Okay. So actually, what we want to develop, guys, we want to develop neural networks that will be efficient, they will have a few, less parameters, and they will achieve better accuracy. So we want to be here, So all the neural network, all the new trends of in building architectures for classification, image classification, is to build networks that will be as smaller as smaller as they can, and in higher value on the y-axis, of course. Questions? Okay, so actually one of the interpretation of the ResNet that appeared in NIPS 2016 is that it's convectional three block residual network building block. Yeah, it's our building block. So we have function f1, we have skip connection, and we continue there. So we continue to the next layer. So if you will see, if you will take a look on the same topology in unrevealed view, that you will see that you have a few connections from the input to output. And actually, what by observing the gradients, what this network, what this paper is observed, that the ResNet are collections of many passes, yeah, and shortest passes are more predominantly contribute to our training, to the result. The gradient there much higher. So the smaller passes, it's there, of course, from here to here, yeah. So these passes have higher gradients and more contribute to our training, rather the longest passes. Okay. Good. Okay. So again, this paper is actually behind ResNet stochastic depth. They see that at training time, each of the mini batch randomly drop of subset of layers, and the test tab use all the networks, yeah? So it forced the network to learn better because we use some inherent regularization. Questions? Okay, so what was the improvement that people proposed on ResNet? So ResNet achieved great results with relatively small numbers of parameters. Yeah, they give all options to do very deep networks, but how we can do it better? So better, proposed by Sergei Zagoroyko, it's wide ResNet, actually very common in your topology. So the difference between ResNet and the wide ResNet is of the number of the features. So actually they propose the same architecture, but more feature maps. Yeah, and they see that increasing feature maps on each block improve the accuracy. Even improve drastically improve the accuracy. Yeah, so this way we can outperform. So what they figure out that 60-layer wide ResNet outperforms 1,000 layer ResNet with much less of the number of parameters. So one of the observations can be here that the wider layers give better observation of feature extraction. Okay. So another improvement on ResNet is ResNet XT. So ResNet XT is actually a little bit have imagination with the Inception model that we actually do our filtration independently, yeah, and then we concatenate between different filtration and got the results. But we have the same complexity because we do not increasing the number of the parameters that we have. We just do it in parallel on different filtration on different feature maps, and then concatenate all the knowledge to one one vector. Okay, so the claim is that increasing the cardinality is the better way to increase capacity than increasing depth or width.
What cardinality means?
Cardinality, it means that you actually taking, that you're dividing you're dividing your convolutions to different. You are looking on different as you are taking your feature maps different aspects of the feature map, like you are each time finding only small part of the feature map, okay, of the extraction. You do the extraction. You do the same the extraction in parallel way. So you are not applying the filter on the all convolutionals. You are doing in each time only on the few numbers of feature maps the filtration, and this it means that like you create some I don't know, some you're increasing you increase the receptive field of how convolution works. Yeah, because you make more convolution. You take care. You give attention, better attention on each pixel. Okay.
Okay.
More questions, guys? Okay, good. So again, ResNet give us rather better results. So from ResNet 15, we have 24 or 76% of accuracy on top one, and here we improve it from the same complexity by around 2%. Okay. Good. So the next architecture is DenseNet. So the DenseNet actually they have even more large connectivity. So it means that residual block we have only a connection between a few layers. Yeah. So only a few layers see the what got previously. Here you have the connection of the all deeper networks have a connection from the layers that are in the beginning. Okay, so actually you translate more and more information and sharing more and more hierarchical knowledge, and this dense architecture is actually give you opportunity to make more deeper networks and achieve even better results. But yeah, I think that the originality of this paper is actually not like ResNet, because they actually only propose some some addition on ResNet, looking more on more creating more hierarchy. Yeah, but again, this actually DenseNet achieve much better results rather ResNet, and with less parameters. Yeah, so this is the ResNet topology. So that's the topology. Again, as you can see, DenseNet even give us opportunity to make a network more deeper. Questions? Questions on DenseNet? Is it clear what's the difference between DenseNet and ResNet, guys?
I think yes.
Okay. Very good. Good. So as we can see here, DenseNet, you remember that what I told you. You want to be in the left side and yeah. So here we actually in the left side. Yeah. This is the we want to be as in Y as small as we can, because it's the error and not the accuracy, and we want to be in the small the number of parameters we want to be, or actually it's the complexity we want to be as small as we can. So DenseNet architectures are much more achieve better results with less complexity rather than the ResNet. Good. Okay. So now you understand how to build very, very, very deep networks, how it works, etc. And what the problems with the vanilla convolutional neural networks. So it means by adding residual blocks, because the problem of the vanishing gradient problem. Now we will talk about the last family. This family is MobileNets. So as you can assume or depict from the name, that we talk about special architecture for telephones or for all embedded systems. For that they actually developed networks that will have a smaller complexity with, of course, great with good accuracy. So, what the key idea of the MobileNet? So the key idea is using depth-wise separable convolutions. We will see what the difference between depth-wise convolutions and the simple convolutions. And the MobileNet model is based on this depth-wise separable convolutions. And we use most of the convolutions are one by one, or the name is point-wise convolutions. So of course, as more you use one by one convolutions, you reduce the complexity of your network. Okay. So yeah, I know it's not a bug. It's a feature. I will remove it. So the versions that you will have will not have this feature. I will upload the version without this feature. Okay, so the standard convolution. Let's talk about. Let's revisit the difference between the standard convolution and the depth-wise convolution. So standard convolution, we are looking on for getting one output feature. We are taking all the input features, calculating the for each feature map. We're calculating the input and making the multiplication, and we have one output feature. So in depth-wise, we actually, for getting one output feature, we only calculate one calculation. We calculate with one filter. So we don't need to calculate m with m filters for getting one output feature map. So it means that we do in factor m less operation for getting for computing our output.
Can you repeat that, please?
Okay, again, in the standard naive convolutions for get the number of operations that you need to do for calculating one output, it's doing the feature decay by m. Yeah, so it means that you need to do for getting first feature map. Results here, you need to do decay by decay computations by m. Yeah, because for getting one, you need to calculate the first input. You need to calculate you need to do filtration for all our feature maps, then making sum, and then we have one output here. Yeah, depth-wise convolution works without taking only by calculating decay by one. You don't for one output, you calculating only decay by decay. You don't need to calculate the various filter values that you have for and summing them for getting one output. So the complexity in the complexity in the standard convolution is decay by m, and here is decay by decay for compute the output feature map.
Okay, but don't I perform more convolutions as a result? Because the feature map is still at depth m, isn't it?
No. Okay, again. So assume that for it's not about the number of feature maps. So for calculating one output here, for calculating output feature first up in first index from the first feature map, yeah, for the first out feature map, we need to perform calculation of our filter here for all the filters that we have. So even if we have filters, we need to perform one this computational of all of them on the various filters, yeah, for getting one output.
Okay.
And here in the depth in point wise, we only take one filter we only perform for getting one output. We only perform filtration one. We do one filtration. We do not take in consideration other filters. So so here in the naive convolution, standard convolution, we need for all output features. We need to make all the. We need to multiply for all filters that we have. Here we do it only independently. One convolution output feature from the one feature map, we only use one filter. Not all the filters are used for calculating the given output.
Okay, thanks. I think I got it.
Okay, if not, I think that I have better visualization in next slide. Okay, so yeah, here I see. So again, so convolution operation. So we have our input channels. We have 3 input channels. We have a number of filters. We have here is 2. So the output channel. So what we are doing for calculating here, we're taking all these convolutions, taking all of them, convolving on all of them for getting one. Okay. Good. And in depth-wise convolutions, it works like that. We taking only one. So for calculating this feature map, we use only this one. For calculating this feature map, we calculate only this one. Okay, so each of them are only so for calculating this one, we only use this feature map. We don't use the other information. Okay, this is the difference, because in the previous we used all of them for calculating.
So basically, we take that regular convolution operation and we separate it into 2 operations. One of them only works.
2 M operations. If we have M feature maps, we separate it to M independent operations and not doing M time each time.
I mean, if you can go to the next slide, you show the point-wise convolution and depth-wise. So if I perform m times depth-wise convolution and then 1 point-wise convolution on them, that's equivalent to the regular convolution that we had before?
Yes.
Okay, thank you.
Good. Okay, so now I revisit what we've seen. So the standard convolution have computational cost of decay by decay. This is our size. by M. By M, it's our input feature maps numbers, and output feature maps number, and df. By df, it's actually the kernel size. So for each the kernel size of for each output pixels, how many input pixels you need to calculate. So in depth-wise convolution, so it's the standard. So depth-wise separable convolutions, we only have decay by m, okay, by df. So we are only for each feature map in output that we have, we do it only once. We do not need to multiply it on n, on our previous number of feature maps layers, okay? So it means that reduction in computation, it's about the factor of n. It's a huge number, okay? So if you use 3 by 3 depth separable convolutions, we got 8 to 9 less computations. So now, is it clear now about the difference between the standard convolution and the depth-wise?
Yes, also it's clear why we do that.
Yeah, very good. Okay, so depth-wise separable convolutions. We in the left we have the standard convolution with batch norm, yeah, and on the right we have the depth-wise separable convolution with depth-wise and point-wise layers followed by batch norm. So this is the architecture. This architecture, of course, much much less computational life rather than this one, as we have seen before. Good, very good. So again, the numbers. So the number of parameters that we have in MobileNet achieve results like ResNet 18 by using 10 times less parameters. So yeah, you can see it actually here. For getting 17% accuracy, only 4 million parameters. Yeah, this is really great. Okay, so guys, I already so it's actually what they done. They use separable convolutions, but what we need for building very depth networks. Elia, Ophir, what we need to, and other, of course, David, Sharon, Olga, what we need to build very deep neural networks?
This layer is the bypass we saw earlier?
Yes, of course, we need to use, we understand that this way stacking, so now we reduced one layer, we reduced layer complexity. We reduced by using the strategy of one-by-one convolution and using depth-wise. Okay, very good, but we can, the gradient, vanishing gradients problem is still here if you want to use, if you want to stack a lot of layers. So MobileNet v2 will address this problem. Okay, so this model takes an input, a low-dimensional compressed representation, and we actually have the depth-wise, and then we have some projection. We actually, the idea is to use the residual connection. So we have here residual connection between the input and the output. Yeah. So yeah, so this is the regular convolution. So this is the separable. This is the separable with linear bottlenecks that we have. And this is the separable with expansion layer. So they add some few more kind of layers for actually better for preventing the gradient vanishing. yeah. So we want to improve the ability of gradient propagate across the layers. Residual connects is only used when the numbers of channels going in the block is the same of the number of channels coming out of it, because we use the same size, of course. Yeah. Good. So residual blocks and inverted residual blocks. So I already talked about it. And this is our model architecture. So in this way, MobileNet v2 proposed to have a very deep neural networks and achieving better results rather than the ResNet, of course. In terms of computational versus accuracy. So yeah, so one important thing that proposed in the MobileNet v2 is using linear bottlenecks. So the experiment, linear bottlenecks is actually it's the way to reduce the dimensionality. So they reduce it not by using these bottlenecks. So it's using linear connections between the layers. So it's actually we can see that linear bottlenecks works much better than using real bottlenecks. So we can understand that from this that non-linearities destroys the information in low dimensional space. So if it works, because this bottlenecks is actually we want to downsample or downgrade our dimensionality. So if you work with very low dimensionality space, using rails there or non-linearities destroys the information that are passing from one layer to other layer. Questions? Okay, good. So here we can see that it is summarizing from performance of MobileNet v2. It's our curve, and this is our curve with different and the other and MobileNet v1. So we can see that from the same complexity we got better results by using this topology. Okay. So MobileNet v3, it's actually the latest architecture, only proposed in 2018, was to replace the last stage of before the classification stage with a more efficient stage. So they propose to replace all these layers from getting 116 feature maps to our 100 vector dimensionality for classification to more efficient one. So it's replaced only from here, yeah. So we replaced all these convolutions from only used by one convolutions in the end, and actually save the computational with the safe computational complexity with achieving same results as MobileNet v2. Yeah. And the performance, of course, we can see the performance much better. The same performance as the MobileNet v2, but with less computation. Okay, so let's revisit a little bit about what we've done, and actually it's this is what we will do next week. So how to use a trained network for a new task? So if we already trained our network, so we now to classify the bot, yeah. So now we can take a vector of activations from here before doing before classification, yeah, and then we can treat it on the shelf as a feature, okay. So and we can train a new classifier on top of these features for another task. So it means that we can have we will see it in other topics in our course. Feature extracting on one data set can help us to achieving results to classify another data set by using the features that we extracting from there, only by replacing the last layer of the optimization. And we do not need to do so. Here we learned on ImageNet, and now we want to learn on another data set. So we don't need to learn from scratch. We can learn on ImageNet, and then only taking these features, plug it in another image in another task, yes, and by of course defining other loss, and then in few iterations we can learn how to classify another data set. Only by fine-tuning. Fine-tuning, it means doing one or a few iterations and not learning from scratch.
Can you be more specific as to which weights on the above diagram we are re-evaluating for different tasks?
Of course. So let's talk. Take us and assume that you have, I don't know, all the weights that you have here. Okay. So you are taking here. You are taking I don't know. We're taking feature space. We're taking features from here. Yeah. From that was trained on it was trained, this model it was trained on ImageNet, and then we want to classify ImageNet I don't know, version number 2. It is other classes. Okay, so what we're gonna do, we will take our images from this new data set. We will share the information that we have in this network to our new network that already we built for we have new network with the new parameters. So we will share this information with the new network, and we will start to do the training not from zero. We already have some features that we detected. So what we actually got, these features, they correlate. They have also information about the new network. Okay, so it means that you can add these features, yeah, or these features at all, for as the initialized features for your new network.
We specifically consider the case where we have the same database but different classes within it.
Again, I didn't understand you.
We're considering the case where we have the same database, the same pictures, for example, but instead of classifying dogs and cats and boats and birds, we're classifying other classes.
No, we are talking about that we have another data set or another task. Yes. You're right. We can define two different tasks. We can define we have the same data set, but we want to classify other classes. Yeah. And the second one that we have a new data set.
And if we have a new data set, we still plug it to the same network, but rework the last weights?
If we have new data set, it means that the same features that you already have on this data set will have some correlation with the new features. Okay, they will help to understand what the feature extraction will work in this way too. But let's emphasize on the task that defined that way. You have same data set, yeah, and you have now you classified 5 classes, and now you want to classify new 5 classes on the same data set. Okay, so you use the features from the first 5 classes, and you actually now will optimize on the new classes that you have by using the features that was found by training the network on the first 5 classes.
Okay.
Yeah. So it means that the features that you find, they're not only specific for these specific classes. They have information about regards the image. Okay. So they can help you also to have information on these images, not independent to which classes you want to classify. You understand? It's like you have a tool how to detect important features of the image, and it's not specific to task oriented. Okay?
Yes, it makes sense. If we use the different data sets, it's plausible to. This is the beginning of transfer learning.
Yes. I didn't. This is why I avoid to talk about this issue. This is the second. The different data set is transfer. It's the start of. It's the first stage of the transfer. It's the transfer learning task.
Okay, so if we were to try and train one network on one database and then use a different database, we would try to use databases that are somewhat, I don't know, correlated, like pictures of faces and other pictures of faces.
Okay, I understand the question, and I will give. Okay, so we will use dataset. We will use the features from the dataset that give very good results. This is why, and very good we want good dataset, labeled dataset, that we will extract good features. So from now, all of the tasks that are not classification, I don't know, detection or other tasks, all of them use pre-trained networks or pre-trained features from using ImageNet, because ImageNet it's like solve that task, and we know how to find a good feature extraction.
Even if the actual pictures are completely different?
Yes.
Okay, that's interesting. Thank you.
Yeah, but again, we will talk. We will give this example when we talk about transfer learning in the most advanced classes. Okay. Good, guys. Thank you very much. Thank you for listening. Of course, the lecture will be uploaded, and the next lecture will be on Monday. What will be in the lecture, information regards the lecture and the time, we will post today later. And yeah, so you will know about what we are going to do there. Thank you very much. Bye-bye.